Probability distributions. Chapter 4 is not all that long either, but there's a lot of very important information in it. We're going to talk about various probability distributions as we go. The ones we're going to talk about, you see various words on there, they're already on your notes. We're going to focus more on discrete than continuous, and most of stats actually is concerned with discrete. You're going to see those two words a lot in mathematics, especially if you continue to go on. We're going to talk about random variables today. It's some numerical value out there assigned to that outcome. Okay? And it doesn't have to be anything overly ambitious. It's just there's some numerical value that's set to that outcome of some experiment that you do. Okay? It's discrete when it's basically finite or countable. I'd say countable is probably the most important word there. I guess finite. Okay? In other words, it can be counted. For example, the number of home runs hit for a season, that's countable. Maybe it was 10, maybe it was 40, who knows, but it's countable. Okay? And the number of outcomes, you could sit there and list them. Okay, that's why it says finite. Because let's face it, there's only a certain number of at-bats in a season, and you could hit a home run every single time, but we could still count how many home runs you hit. Right? If it's continuous, it's infinite number of possible outcomes. I look at it this way. I think of this one as counted. This one is measured. That's kind of how I look at it. In another way, that's kind of a little bit more outside the bounds of statistics, but just in general, I look at the two as discrete, being, this is the number, this is what it is. Okay. Then the next year, it could be some other number. And you don't have to worry about all the numbers in between those two. All I'm concerned about are those two numbers, right? And if you graph that, do you agree it's a point here and a point over here, right? They are not connected, correct? For continuous, I kind of feel, for example, that could be, let's say I lost some weight. I started at 180 pounds and I ended up at 170. Do you agree that at very minimum, all the other weights in between 170 and 180 had to happen at some time? Do you agree with that? There's no way I just automatically woke up the next day and I just lost 10 pounds, just like that, split second, lost 10 pounds. That doesn't happen, right? All of those numbers in between had to happen at some point. How about those home runs? Let's say in one year they hit 40 home runs, the next year they hit 10. Did I have to hit 39 home runs? Did I have to hit 38 home runs? No, I didn't, did I? So that's kind of the difference between discrete. If you graph that, there's two distinct points. Where continuous, if you think of graphing, is you can graph it without picking up your pencil, right? Do all those weights have to happen in between at some point? They do, and so that kind of is, again, outside the bounds of necessarily stats, but that's how I look at it. Are all of them in between? They kind of have to happen in that case. Again, which ones are we going to deal with most? Discrete or continuous? We're going to talk about discrete for the most part, okay? So again, I think if you look at these two words, I think you'll be all right. Counted or measured, okay? Because as I said, there's some interval on there, okay? So for me, that interval I'm talking about is 180 pounds to 170 pounds. That's an interval, correct? Somewhere in between there is where my weight was, okay? So let's see if we can figure it out. The random variable x, is it discrete or continuous? So x here represents the volume of bottled water in a 32-ounce container. So what do you think? There's a 32-ounce container maybe sitting on your desk. Could you have 2 ounces in there? Could you have 30 ounces in there? Can you pretty much have anything from 0 to 30? Because if you go over 32, it's going to pour out, right? So you can go 0 to 32, right? You can have any of them, right? And the next day, and let's say if I try and pour that out to get some out, along the way, aren't all the other measurements in there as well? Okay, so that is most definitely continuous, number one. Okay? So I'm trying to give you all the different types of ways of looking at those two words. Because again, you're going to see those two words a lot if you go on in math. X represents the length of time it takes to complete a test. What do you think? Why would you say continuous? Okay. Here's one where you might want to say, is there some kind of range? Is there an interval? Could it take me 0 minutes to take a test? No, if you don't do anything on it, yeah, it took me 0 minutes to take the test. There you go. Could it take you an hour to take the test? Are all other possibilities in between possibilities? They are, aren't they? They're all possibilities. So that one is continuous. And pretty much whenever you see time, that should be a good tip of the hat, that's more than likely going to be continuous. Because once you get to calculus, continuous kind of means sometimes more with time involved. Okay? And how about X represents the amount of points scored by a basketball team in one game? Yeah, you add them up, you scored 50 points. Done. 50 points scored. Okay? In the next game, you scored 60 points. Did you have to score 52 points in one of the games? No, you can go from 50 to 60 without hitting all the ones in between, correct? If you're talking about two completely separate games. Okay? So can you come up with another discrete? What's another one? Because continuous, I think we get the idea, and it's not one that we're going to focus on all that much, but discrete we are. So can you come up with another possible example of discrete? Yeah. Okay, number of runs scored by a baseball team. Yes, ever so clever to use the same idea. Okay, but do you get the idea between the two, the difference? Okay, and a lot of times in other math, how you deal with them, you have to deal with them differently. And same thing here. Discrete is the ones we're going to focus on, though. I don't think we're going to touch on continuous all that much. Okay. So if we have a discrete probability distribution, so you had to know the difference between the two, so you knew what we were talking about. List each possible value the random variable can assume along with its probability. So we're going to say, for example, the roll of a die. Could you list all the possible values? If you roll one die, you could get a 1, you could get a 2, you get a 3, 4, 5, and 6. And could you very well list all the probabilities along with them? Yeah. Now we're assuming a fair die. I could always weight one side, and then it's not going to be fair anymore, right? But if it's a fair die, you could list all those probabilities. So a probability distribution, though, they have to follow two rules, and they're very simple rules. Do you think you know those two rules? You probably know them. What are some things that have to happen in a discrete probability distribution? Okay, what about all the possible solutions? What if you look at their probabilities? Close. This is something you know. I know you do. Doesn't each probability have to be between 0 and 1? Again, there's a notation at the end there for you if you prefer that one, but you knew that. Okay. Flip of a coin. Heads is, assuming a fair coin, heads probability is half, tails is flipping a coin a discrete probability distribution? Mm-hmm. And so think of that coin flip again. Heads was what? Half, tails was half. Are those all possible outcomes? Half, half. No, they're not equal because the roll of a die. I mean, I could tell you if I give you an unfair die or if I give you an unfair coin, it could be 3/4 and 1/4. But they do have to add to equal 1. Again, it'd be very simple to do that. Just put weight on one side or the other of that coin, and it's not going to work out quite right. In fact, there's been some studies that believe that the head has just a little bit more weight on it than on some coins, which does make tails happen a little bit more frequently. But there have been studies that they've actually done the weight on both sides, and they think because some of the heads bow out a little bit, the foreheads, they say that maybe there's more weight on that side, which would mean that it would go down more often. But then, of course, it all depends on if the person flips it after they catch it, or if they just let it land. It all depends. Yeah. That is a good question. The question was, is that why they say if you find a penny where it's face up, it's lucky? Is it? Because is there more weight on the head, and should it truly be facing down? Good question. When there's more weight on the body, the more weight's going to want to go down. And when you flip it, it might bounce around for a while, and that more weight, the head's going to try and go down. Exactly. The weight of the head is going to make it want to go down. Yep. For example, if I had a die for you and I put more weight on, say, the 6, you're going to see a lot of 1s because that's opposite the 6. Because that 6 is going to want to go down. Okay? I will. I'll get you some. I'll show you.
Like shape out.
No, I'll show you. Not today. I will have to get to the number cubes. So we're talking discrete here. So an industrial psychologist administered a personality inventory. That would be interesting to do here. For passive-aggressive traits of 150 employees. Individuals were rated on a score of 1 to 5, where 1 was extremely passive. Does everybody know the difference between passive and aggressive? Everybody?
Passive, you don't do anything aggressive, you're very...
Yeah. Okay. And 5, extremely aggressive. A score of 3 indicates basically medium or neither trait is being shown for that person, okay, because it's in the middle, right? The results are shown below. Construct a probability distribution for the random variable x. So how do we know it's discrete? Well, it's either a 1, 2, 3, 4, 5. Can I list all possibilities? I can. And the frequencies are given right there, 24, 33, 42. So there's 42 that had a 3. And how do I know that the total is 150 there? That sigma there, sigma f 150, how do I know that? Well, it's 150 employees, right? So it better be 150 total, right? So how are you going to figure out those probabilities? Yeah, to find out this one, you're going to take 24 and you're going to divide it by 150, right? To find out that first one. So 24 divided by 150 would be that number, so forth and so on. And if you do that, hopefully you get 0.16. So why don't you go ahead and calculate some probabilities here real quick. I know, he's doing work on a Monday. Terrible. All right, let's see what you did. This is what I got. For your probabilities, I divided them out. That's what I got. I got 0.16, 0.22, 0.28, 0.20, if you wanted to put that, and 0.14. Okay. And then what did we say? So are all these probabilities fitting the rule? Are they between 0 and 1? Yep. And so watch out with rounding. Obviously, if there is some rounding, there could be possibilities with that being exactly 1. But obviously, if you get 0.99 or 1.01, those are fine. You get too much further out than that, then there might be a problem. And that's where I have a slight issue with one of the book's examples. But for the most part, they should be very, very close to 1. Okay. Well, there you go. So it is definitely discrete. And we're going to need that information for a later example, so that's why we had to figure that out. So do you believe that these are probability distributions based on the rules? How about letter A? Are they all the probabilities? So your random variable x could be a 5, a 6, a 7, or an 8. Do we know what this is? No, but we know it could be a 5, a 6, a 7, or an 8. We got 0.28, 0.21, 0.43, and 0.15. Are those all between 0 and 1? So we're good on that fact, right? But I do believe if we add them up, we get 1.07. Now you're going to get to a point, is that close enough? Is it not close enough? I would say for our purposes right now, if it is not exactly 1, we'll say no. All right? And so that's 1.07 if you add them all up. So this one is unfortunately no. So all of these, they're good. They're all between 0 and 1, but it adds to 1.07, so that's no good because it's supposed to add to be 1. Okay. How about that one over there? That adds to be 1. Yeah, one of my probabilities is over 1. And 1 is, what's the probability of -1? What does that mean? You know, I mean, how do you tell? What does that mean? And how do you have a probability of 125%? All right. So this one is no, because not every single one of them. This one can't even happen. So this is also no. All right. Because those can't even happen. All right. So any questions so far about a probability distribution? No? All right, we're doing great then. The mean is actually quite simple. How come they chose mu instead of x bar?
Population. It's all.
How do you know it's all? Okay, it's discrete. What does that mean? There's a set number. It's finite. It's countable. So if they're countable, are you going to have the entire population? Yeah. Okay. So mu, that's why they chose mu right there. So sigma again. So all you have to do is take x, your random variable, times its probability, and add them up. Well, okay. Sounds good. So let's use the same one that we have from example 2. You already have all the numbers, don't you? So just write them in again. You already have them, right? Oh, look at that. It adds to 1 again. Imagine that. You already have those numbers. So then this is saying to take x times its probability. Well, here's your random variable of 1. Take it times its probability. Well, that's an easy one, right? Okay, that's very simple. You take 1 times that, and you get 0.16. If I take 2 times that, I'll get my next one. That's also an easy one, right? How come these numbers are getting bigger? Well, I think here the random variable itself is getting bigger, okay? Because they're saying the score of 3, and they're saying that 28% of them scored a 3. All right, the 28%'s over a quarter of them, so that's where a lot of your data is going to be, right? And so there they are. Now, of course, we could go back, and to find the mean, we could always find out, okay, how many of them answered 1? Well, we got that many of them. How many had a 2? Okay, we got that. And then divide by how many people we had, right? Well, this just takes too long. And let's face it, we already divided by how many people we had to get this answer. So all you have to do is add those up. And that will tell you the mean value. What do you think that is about? Where would you guess it would be about? If your possibilities are 1, 2, 3, 4, and 5, do you think the average is 5 based on the probabilities you see here? Where would you say the average is? Pretty close to what? 3. Do you think it's going to be above or below based on the numbers you see? I'd say below, because these two numbers right here, 0.16 and 0.22, are bigger than the 0.2 and 0.14 that are below. So I'd say it's going to lean the values to be less than 3. Do you see that, how that works? Because if you were to graph these, and I think maybe we'll do that in a second. In fact, is it on here somewhere? Maybe I did that. I don't know. Oh, no, I think we're going to talk about that some other day. It would be skewed, right? This would not be symmetric. It would be skewed. And what'd you get? Do you agree with that? That the average is about 2.94, based on what you see here. A lot quicker way to do it, isn't it? Because we could have gone back here and said, okay, so we got 24 of those, we got 33 of those, and keep going it that way, and then divide it out. But it's a lot quicker just to say, well, if that's the probability that it's going to happen, or how the distribution worked out, well, 2.94, yeah, that does make sense to be the average of these, right? I mean, it makes sense. So on average, this group is neither passive nor aggressive, right? On average, we would say. And in fact, we would say they're more towards the passive. Not by much, but they're more towards the passive. Variance and standard deviation. Boy, we've heard of those before, right? Why do we square those differences again? Yeah, we don't want the negatives to go away. Because what happens if we just did x minus mu and just kept going and added them up? Yeah, we'd get really close to 0 depending on rounding, right? Right? And so we square them to get rid of it. And why don't we use the absolute value again? Because that would get rid of it. Yeah, I remember the median. That's what a median is the absolute value. That could have many answers, right? Where this one, it's a parabola, right? How many? We're trying to minimize things, right? We're trying to find out it only has one answer. So that's why we square it. So they're saying what you have to do is basically find that difference. Well, we're used to doing that. Square it, okay? And then take it times the probability. And then what's the sigma tell you to do? Add them all up. All right, so then the standard deviation, of course, is the square root of that. Because if we ended up squaring things, well, we got to get rid of that, right? Because variance itself really isn't as valuable of a number as you would think it is. Okay? The standard deviation is hugely important. All right, so calculate the variance and standard deviation for that inventory. Well, good thing we figured out mu. 2.94, right? I think I even put it on your little table, didn't I? Or no, I did. So let's find out what the difference is. And here's where Excel could save a ton of time, right? I mean, you just sit there and do it. I think we can all do this, so let's just get the numbers in there. I don't think all you do is you take, well, here all I did is I took 1, right? That's what x is. That's 1. That's the random variable. Whoops. And I subtracted the mean. I got negative 1.94. Do you agree with that? Right? And then I took 2 minus that. Well, obviously that's that number. 3 minus that. Well, that's obviously 0.06. 4 minus that is 1.06. I'm hoping this follows pretty easily for you. Would adding up these values help me at all? Not really. Why not? Yeah, it should be really close to 0, and obviously we did some rounding, so I don't know if it actually comes out to that. But yeah, those numbers don't help me at all. So then what do I got to do for the next column? I'll square those numbers. All right, well, there they are. Again, this just saves you some time. Obviously, I could have you calculate this, but I think you all can handle these. I'm more worried about the notation, to be honest with you. So I think maybe the last column, I will have you go ahead and calculate that. So you have to take that squared, I guess, difference, you could say, and take it times the probability. So why don't you go ahead and do that? I'll give you a little time. All right, let's see what you came up with here. That's where I chose to round. Maybe you went a little further out, a little shorter, whatever. I came up with 1.616-ish. So how's that number help us? It is the variance. Very good. So what's that number tell us? Yeah, it doesn't tell us much at all, does it? But if we take the square root, it tells us a lot. Because if we take the square root of variance, you get standard deviation. Again, how much you would expect. That's one standard deviation, again, right or left. It's about 1.27 if you take the square root.
What is standard deviation again?
About how far you would expect a value. So if you picked one at random, you would expect it to be within 1.27 of the mean, or be within 1.27, you know. Right. Okay. And so what I want you to take a look at, and the reason I spent some time with Excel, I know you didn't see it on the recording, but I was doing it here, is that if you look at the histogram of this, does that make you believe that the mean is just a little less than 3? Yeah, because this is skewed, right? Barely, not much. It is very close to symmetric, agreed? It's very close. But it is definitely that way. And what they're saying is that if you picked an individual at random of those 150 individuals that were surveyed, you would expect them to be within 1.27 of the 2.94 if you just picked them randomly. Do you agree that that would be a good expectation? Yeah, probably pretty good, isn't it? Based on where everything was distributed. A probability distribution. Okay, this one is very close to the one of your other teachers likes to talk about. Okay. We'll be starting looking at various things like that as well. So a lot of notes today, but again, no assignments, so that's all right. Expected values, really big. And then what would you expect to get? And the nice thing is, in the discrete random variable, it's basically equal to the mean. Okay, so how about that personality inventory test discussed in 2, 4, and 5? What would the expected value be? 2.94. We already calculated the mean, right? Okay, and how did we do that? Well, it was pretty complicated, and we'll do that on the next two. I'll show you how that's actually done. So that means, basically, in that case, if I kept having people take that test, I would expect them to score 2.94. Okay, is that even a possible? Is that even a possible score? That's not even a possible score. So how could it be the expected value? Well, that's how this one works. That's how expected value works, and I'll show you in the next couple how that works out. So how about one roll of a fair-sided number cube? What's the expected value? This is one that you might struggle with. It's not even a possibility. It is 3.5. How do you expect somebody to roll a 3.5 on a number cube? Okay, yeah, it is just, look at it this way. I look at it this way. I could get a 1, agreed? And what's the probability if it's a fair die? It's 1/6, right? Plus, what's the next possibility? 2 times. This is really what we should have done. And isn't that what we really did up here? I just gave it to you in a table. Didn't we take all possibilities times their probability and add them up? That's exactly what we did. But seeing it's a fair-sided, they all have the exact same probability, couldn't you just add them up and divide by 6? So really what we did is we factored out the 1/6 and then we just added them up. That's how you're used to doing it, correct? That's because they have all the same chance. Don't you agree it's the same thing? Okay. So it is 3.5. You could look at it this way. Let's say if I kept letting you roll, how should I say it? This might work. We'll see if this makes sense to you. I'll let you roll the die. If you roll an odd, you give me $1. If you roll an even, I'll give you $1. If you keep rolling over and over and over, no, that's a bad example. I'll come up with a good one of why the 3.5 would make sense. Yeah, one of these days I'll come up with a good one. Yeah, I know that was a bad example. I'll come up with a good one. Right. So my examples. I'll come up with a good one. Just give me a chance. I'll come up with a good example. Yes. I took all those answers right there and added them up. Well, basically, I took 1, which was a random variable, times its probability, which was 1/6. Then I did, 2 is a possibility. I took that times 1/6. I took 3 times 1/6. I took 4 times 1/6, and then I added them all up. But really, we're used to just adding them up and dividing by how many we had, but that's because we're always expecting that there's an equal possibility of each one. And we're going to find out on this next one that doesn't always happen. Just like example A there, it didn't happen there either. It was a 16% chance and a 20% chance, a 22% chance for those scores. Okay, so the expected value does change a little bit. So it really is just the average. But if you're at a raffle where there's 1,500 tickets that are sold for $2 each, and there's only 4 prizes given out of 500, 250, 150, and 750, you bought 1 ticket. What is the expected value of your gain? So what do you believe you're going to gain? What's the expected value? So are you expected to win $500? No. Well, we can't quite do that on this one. So let's do the winning this prize. What is your gain? You get gain. 498, right? That's how much you would gain. You see that? So 498 is one of the possibilities correct, right? And what is your probability of winning that? Right? That's your probability of winning that. Plus, what's another possibility? Possible gain. There's another possible gain. You're not going to gain $250 because you had to pay $2 to get it, right? So you would gain 248. But again, we're just talking, what's your probability of just winning that one? No, just winning that one. Yep, don't even worry about it. It's 1 in 1,500. Is your probability of winning that one, right? One person out of the 1,500 is going to win that. Plus, well, 150 is next, so 148 times, and only one person is going to win that. Plus 73, and one person is going to win that one. Why did I put plus? Ah, is -2 a possibility for a lot of people? Isn't it? Is that one you forgot about? Almost definitely. -2. Now, is that your gain? Well, yes, I gain -$2 is what I gain, right? Very good. 1496 out of 50. How'd you come up with that number? 1496. There's only 4 prizes, so how many people are going to gain -$2? Well, 1,496 people are going to gain -$2. Lucky them, huh? And we don't have to add this up. I'll save the time. Expected value is to lose $1.35. Well, isn't that lovely? And I'll come up with a really good example for that die.